Good morning, everyone. I'm Pulak from NCRA, and as the title suggests, I'll be talking about the Magnetar that Yogesh briefly mentioned yesterday. Specifically, I'll be talking about the narrowband emission from this Magnetar. These are my collaborators, and I would like to thank them immensely for their contributions that gives shape to this work. To begin with, we know that fast radio bursts or FRBs are short millisecond duration, bright extragalactic bursts. We know that the emission is coherent, but I can assure you that our understanding about the emission and the progenitors is not very coherent. And as Paz motivated in a very beautiful way, that magnetars are currently the leaders in the race of the progenitors, especially after FRB like burst was detected coincident with a galactic magnetar. This basically suggests that some FRBs, if not all the FRBs, share a magnetar-based progenitor. Now, studying such potential progenitors that we have in our galaxies, will not only help us draw some phenomenological links to the FRBs, but also by studying the spectral, temporal, and polarimetric signatures and comparing them, we can get insights into the emission mechanism. One such intriguing property that we see in FRBs, especially the repeating ones, is their interesting spectral structure, specifically the band-limited emission, which we know is not caused due to scintillation. And in addition to that, we see some complex spectral structure as well, such as the downward drift. Now, this brings me to the magnetar of interest today that I'll be discussing. So this magnetar is commonly known as J1810-197, was the first magnetar to be discovered in radio frequencies following an outburst in X-ray. And after that, the emission ceased after 3 years. The magnetar then reactivated emitting in radio in December 2018 and has been constantly monitored since then. What makes this magnetar interesting, especially given the context of this work, are the spectral features which share some morphological similarities to that of the FRBs, especially the band limitation. And there are only a few galactic objects that show these features, which are not explained by scintillation, as was described earlier. So to make stronger claims and draw connections from the magnetar to the FRBs, and to add this to the list of these limited narrowband galactic emitters, we need to first rule out scintillation rigorously. So preliminary analysis shows that the scintillation bandwidth, which is estimated from the measured scattering time, turns out to be less than 1 kilohertz. There is some issue here. Turns out to be less than 1 kilohertz. And it was actually measured to be 150 hertz in a recent paper by Marthi and Maan. And this is also supported by the electron density models. So everything is good. We can say there's no scintillation, but what complicates the fact is the possibility that there could be two screens. Say there is the first screen that has given the scattering time that is measured here, and we are inferring a small scintillation bandwidth that is coming basically because of this screen. But there could always be another screen which has the scattering time so small that it will not be able to measure it given the finite resolution of in our data. And this could give rise to a larger scintillation bandwidth, which could again explain these spectral features. So it is very important to test the scintillation hypothesis rigorously before making any strong claims. With this in mind, we have will be using the data from GMRT. As mentioned earlier, it was constantly monitored after the outburst in 2018, and we'll only be discussing a subset of epochs. So we'll be discussing 5 epochs from December 2018 when the object reactivated to February 2019, and the rest of the epochs are currently under analysis. And we are using the band 4 of GMRT to make this analysis. So the goal of this project is as follows. First, we have written a pipeline to search for these signals with such spectral features, And we have done this because what conventional search algorithms do is that they do the single pulse search after averaging over the entire bandwidth, and this has the tendency to miss the narrow and faint bursts. Once we have the burst, we need to characterize the spectral nature, and obviously we need to compare them and see whether it is consistent with scintillation or not. Now, as mentioned earlier, say you have a burst, a narrow and faint burst like this. What conventional search pipelines will do, they'll average over the entire band, then generate a time series. And say if you have a threshold, signal to noise rate threshold of 8, this burst will go undetected in the conventional search. But if we just search it in subbands, like if I just average over this subband to generate the time series, suddenly the burst becomes detected. So this is going to be the base which we'll be using for our search pipeline. As shown in this example, the search is also sensitive to the width of the subband, considering when the width of the subband is of the same scale as the emission bandwidth, then we see that the signal to noise ratio is the highest, and if you have widths lesser than or more than that, the signal to noise ratio decreases. So in this particular search, we'll be searching over subband widths of 12.5%, 25%, and 50% of the bandwidth. And obviously, we need to move these subbands throughout the bandwidth so that we are sensitive to the position of the bursts as well. Now, as shown in this figure, which is the plot of the signal to noise ratio as I keep moving this subband, we see that for a single real burst, we are getting multiple detections here, and the condition worsens if you have a brighter and a broader burst. Say this burst was 4 times brighter and 2 times broader. This will give rise to 22 duplicate candidates for a single real one. And the situation complicates further if we consider the duplicates in time. So a proper sorting algorithm is necessary to just remove as many duplicates as possible. I'll not be going into detail of this, but you can catch me offline and we can have a discussion. But more or less, the algorithm basically compares the overlapping subbands and checks for duplicates. But while doing this sorting, we encountered a problem, something which is an arch nemesis for all the radio astronomers, which is RFI. And the RFI not only messes with our filtering algorithm because they have broader widths, but also they result in a lot of false positives. So to tackle this issue, we have used Fetch, which is retrained by Ankit. So Ankit is here, he's a lovely person, feel free to talk to him. And so he basically retrained Fetch using narrowband bursts, and we saw improved performance from 78% to 95% on narrowband bursts. Now, once the sorting is done, what we are left with is a list of narrowband candidates. Now, before doing the fitting, we all know that when you have a noisy data, the fitting is extremely sensitive to initial conditions. And to determine the initial conditions, initially, we are first we'll generate the dynamic spectra using a BFF written by Yash. And then we'll be using a YOLO, which is an object detection model, to identify these bursts, again trained by Yash. And once we have a pretty accurate initial condition of the bursts, we fit the spectra using these initial conditions. Now, these are the results. So basically, after this fitting is done, we are left with 2 parameters for each of the bursts. First is the emission bandwidth for the burst, as well as the central frequency of the bursts. So if we take a look at the emission bandwidth of the bursts, we see that out of the narrowband candidates, they are very narrow, and the bursts have a median of around 60 megahertz. When we take a look at the histogram for the central frequencies of this burst, we see that most of these bursts appear in the upper part of the band, and we see that the median to be around 700 megahertz. We have seen this consistently, this preferred frequency over duration of 2 months, which is our last 2 epochs are separated by. So this I'll come to later while discussing about scintillation. And if we make a plot of the scintillation bandwidth with the central frequency, we see something like this. So firstly, these spurious artifacts are because of the band edge effects. Then we see a trend like this, which we believe could be intrinsic. And then we see a taper like this, which we think could happen because of the limitation of our observing bandwidth. So since we have a limited observing bandwidth and say a burst is going, a fraction of the burst is going outside our observation bandwidth, the estimated bandwidth, emission bandwidth will be much lesser than the true one, which could give rise to a taper like this. We looked at how the rates of these narrowband bursts vary with epoch, and we see that near the onset of the burst of the reactivation of the magnetar, we see that the rates of these narrowband bursts are very high, and as for the later epochs, we have seen a lesser number of bursts. Although there are there is data in between this that we need to analyze to see if this trend is gradual or it is sudden. If we compare the burst properties of the as a function of epoch, we see that in the initial epochs the bursts are narrow, as well as the distributions of these bursts are also narrow, as is shown by this violin plot. We also tried to search for some pattern in the pulse with the pulse phase. So here is a plot of the central frequency, so the emission bandwidth with the pulse phase for 2 epochs, and we don't see any pattern here. The same thing goes for the central frequency also. We don't see any pattern of the central frequency with the pulse phase. Now, to answer the question that we initially asked, whether this is caused by, these features are caused by scintillation or not, we clearly, as I mentioned earlier, we clearly see this preferred frequency over epochs separated by 2 months, and diffractive scintillation does not predict such preferred frequency, especially given the time scales of diffractive scintillation is much smaller than 2 months. Moreover, the scintillation theory predicts a power law relation between the emission bandwidth, the bandwidth and the central frequency, and we see that relation is plotted here, and we cannot conclude. We see some deviation from this pattern, but again, this is not conclusive. But since we have some candidates having multiple narrowband components, what we can do is that we can look at these candidates and see if these candidates individually follow this pattern or they strongly differ from this. So these are some of the patterns having some of the candidates having these narrowband components. And if we take a look at their emission bandwidths as a function of frequency, we see that the trend is completely opposite to what we expect for scintillation. So now basically we have evidence suggesting that these bursts are intrinsic or could be because of some propagation effect like plasma lensing, but we are in a position where we can say it is most likely not due to scintillation. Now, if not scintillation, these band limited emission can be caused by, say, plasma lensing, could be due to absorption, which looks to be unlikely in this case, or it could be related to the underlying emission mechanism. There's this review by Yang et al. 2023, which gives a good review for the reason of the narrowband emission. Now, to conclude, so FRBs have very interesting spectral features, and band limitation is one of those, and they can give insights to the emission mechanism. And the magnetar that we have discussed here have also exhibited such features, and studying these features could help us draw a phenomenological link to the FRBs. But firstly, we need to say whether this is scintillation or it is not. To answer this question, we have firstly developed a pipeline to search and characterize these narrowband pulses. And the preliminary results suggest that these features are not due to scintillation using time scale as well as the expected relation arguments. All in all, this establishes a phenomenological link with FRBs and can shed some light on the emission mechanisms. Thank you.
Thank you, Pulak, for the interesting talk. And any question, Bailey?
Yes, thank you. Just a quick comment on the scintillation. You cited a 1985 paper, which I think I just explained. The field has moved on. There's a local expert, Visweshwar, up here, who will be happy to explain. It was VLBI. We know that none of that story is relevant, and it's all due to discrete plasma images and not due to a diffraction screen, and therefore the scaling of 4.4 is not expected. So I think we understand much more, and I'd be happy to explain more, but I think it has moved on.
Yeah, but
5 is too old.
But we still do expect a polar relation. It might not be 4.4, but
No, you do not. Sorry, you do not expect that. Quarters 85 is ancient. It's 40 years old. That is irrelevant today. So please do not cite these old papers. They're irrelevant, and the expectation is incorrect.
Right.
Any other questions, comments? Yeah, please. And probably Vansi, the next speaker, can come here down and prepare for your talk. Yeah, so please, Usha.
You saw most of the bursts at your upper end of the band. Did you look at the band above as well? Search if you see even more bursts, or if it's going down?
We do have some of the observations simultaneously in 2 bands, but yeah, we have not yet looked at them. We need to analyze that.
Okay, thank you.
Okay, great. Then if there's no more question, let's thank our speaker again. Thank you.